Okay, this will be the lecture for Chapter 19. It'll be on DC circuits. What I'll kind of start off with talking about is this, funny little creature called EMF. It's kind of funky, but hey, we have to work with it, as well as terminal voltage across a battery. And then we're going to be looking at a whole set of circuits. We'll be looking at circuits that are in series and parallel, and just kind of changing out components in them. So first we'll look at them with resistors. Then we'll look at EMF in series and parallel, and we'll look at capacitors in series and parallel. Super important part of this lecture is going to be on Kirkov's rules. And we'll talk briefly about RC circuits when we hook up a circuit that has both a resistor and a capacitor. And lastly, we'll talk about how we measure current and how we measure voltage, as well as possibly some electrical hazards. Okay, EMF. EMF stands for electromotive force. Electromotive force. Really, it's just kind of a generic word for voltage, but really it says, hey, we can get voltage or EMF from a battery or a generator or a whole mess of different ways. So all of these are called sources of EMF. Now, it's kind of written with this little kind of squiggly E right here, and something to keep in mind is suppose we have just kind of an ideal battery, and I'll kind of draw the positive side here and the negative side here, and this battery is going to be labeled, let's just say 12 volts. That's going to be equal to the EMF of the battery. However, the batteries are going to have some small internal resistance to them. So if I wanted to say, hook up something to it and measure the voltage between A and B, I have to take into account the fact that this battery has got some tiny little internal resistance, which, let's just say it's going to be 0.1 ohms. Now I can go ahead and I can measure my terminal voltage, VAB, which is going to be the EMF of this perfect battery, 12 volts, minus the current flowing through the circuit. Let's just say I have 10 amps for the sake of an argument. 10 amps multiplied by the internal resistance. Again, that's typically given a small r compared to a big R of 0.1. So my terminal voltage is going to be 11 volts rather than the 12 volts, which is the EMF of the battery. Now, whenever we kind of look at this on a circuit diagram, maybe we're going to see some wires connected up to a circuit. I'm going to say, alright, well, it's still going to look like it has a positive side and a negative side, so a long wire and a short wire. Then you're going to see kind of this little squiggly looking thing, which is going to have a little R associated with it, and that's going to be some internal resistance. What that's kind of saying is if we have a circuit where we have some voltage source and we have some resistance, then we're going to treat it as having a terminal voltage, which again is going to be the EMF minus the current multiplied by that little resistance. I like to kind of think of it as, here I'm on terminal B, I'm going to walk across this battery, I'm going to gain 12 volts worth of power, shall I say, and then I'm going to lose some potential because I have to go across this resistor. This resistor is going to eat up some of my potential, which is going to be equal to the current, using the example from the last slide, multiplied by the resistance of 0.1, and again I get some terminal voltage that's different than my EMF. So now let's take a look at hooking up circuits with, in this case we're going to be hooking up resistors in series. That little squiggly guy right here is going to represent a resistor in a circuit diagram. So if we've said that it has some resistance R1. Now here we have our EMF source. Since it doesn't have an internal resistance, it's just going to, the terminal voltage is just going to be the same as the EMF, so we just write a single V here. And we know that current is going to flow away from the positive and essentially coming over here back into the negative. Now think back to the water pipe analogy. The current right here must be equal to the current right here, and there, and there, and there, and so on and so forth. So the current across all of these resistors is going to be the same. It's going to be I. It's going to be in that direction right here. Now these resistances may be different, and so what that means is I'm going to have different voltage drops across this resistor, where I can calculate this voltage to be equal to the current multiplied by its resistance, This one may be a different resistance. The current's going to be the same, so it's going to might have a different voltage drop, and kind of the same right here. Now, the important concept for resistors in series is that the current is going to be the same through each resistor, so keep that in mind. The voltage drop is going to depend on the resistance, and actually it turns out that if we were to add all these voltage drops up, V1, V2, and V3, they should equal to the voltage of the battery. So if the voltage of the battery was equal to 10 volts, and the voltage drop 1 was equal to 3, the voltage drop 2 was also equal to 3, so it must have had the same resistance, then this voltage drop must be equal to 4. What we can also kind of do is say, hey, look, the current must be the same, and so I could actually go ahead and write this guy to be equal to, the voltage is equal to I, R1 plus R2 plus R3, where I've essentially used Ohm's law for R1, R2, and R3. Now, what this kind of means is I could actually say, hey, you know, I can treat these three resistors to be some equivalent resistance. So I could say, hey, my potential is going to be equal to the current times some equivalent resistance. This equivalent resistance is simply going to be the sum of all the individual resistances. And very typically what happens is we're given values for R1, R2, and R3, and we're given a power source, say it's 12 volts. What we then kind of do is say, okay, well, let's add these guys together, get some equivalent resistance, and figure out how much current is flowing through this circuit. And then we hop back and say, okay, this amount of current must be the same across all three resistors. I could actually go back and calculate the voltage drop across them. So resistors in series, we're going to add them together just like this. And if we had R4, R5, R6, we can kind of tack on, just keep on adding those guys together. Now, the other way we can hook up resistors, or pretty much anything, is going to be in parallel. And essentially the important thing to remember for parallel is the voltage across each resistor must be the same. So here we have a battery, we're going to have our current flowing out right here, and then we're going to reach some junction, and then the current has three paths that it can kind of choose, 1, 2, or 3. It's going to kind of meet back up at this other junction, and suppose that this is simply 120 volts. I know that I'm going to have 120 volts across each resistor, so that's kind of the key to solving these guys. Now, kind of conceptually, current's going to take the path of least resistance, so if R1 is going to be, say, the smallest, then I1 is going to be the largest, and if R3 is very, very large, then I3 is going to be the smallest. What we'd like to do is we'd like to essentially be able to boil this down into some equivalent resistance like we did with series, and then say, hey, we know that V is equal to I times R equivalent, and once we know what current is flowing through this guy, because very typically we're given R1, R2, and R3, so we could say, I can solve for, if I know what this equivalent resistance is, I know what the voltage is, I can solve for the current flowing through these guys. Well, it turns out that I can write the equivalent resistance is going to be written as such, where 1 over the equivalent resistance is going to be 1 over R1 plus 1 over R2 plus 1 over R3, and so on and so forth. Keep in mind that when you solve for this guy, we have to remember to flip the end result over. We have to invert 1 over REQ at the end of the day. So much like I said on the last slide, you can write the current at the end of the day is going to be the voltage divided by the equivalent resistance. Something else to kind of keep in mind is charge has got to be conserved, and so current, as I approach that junction with some current I, it's going to split into 3 different paths. We must be able to write that current as the sum of those 3 individual currents, because some of it goes into this one, and this one. The amount of charge, the amount of current is going to be the same. And again, I can write my voltage in this slightly more complicated looking equation down here. And once again, we can write the equivalent resistance as such, and just so that way you know kind of what I'm talking about. Suppose I've got 3 resistors, and I'll just say for the sake of argument that they're the same, it's going to be 10 ohms, then my equivalent resistance is going to be 1/10 plus 1/10 plus 1/10, and that's not going to be equal to REQ. The equivalent resistance is going to be 1 over REQ. And so 1 over REQ is going to be equal to 3/10. So make sure I flip this guy over and I say that REQ is going to be equal to 10/3 or 3.3 repeating ohms. It really is helpful to think about water when we talk about series and parallel. I like to kind of think of series, you kind of take two pipes and you stack them together. The same amount of water, the same current must be flowing through both of these resistors, and really the short pipe is going to be the resistor with the most resistance. Resistance is going to add up. If we want to consider the case of parallel, I like to think of this water being at some height, it's got some voltage. That voltage is going to be the same for both of these two pipes, but water can take different paths. And so if this pipe is mostly clogged up, then not a lot of current is going to take this pipe, and more of it is going to take this pipe over here. So for parallel, remember that the voltage is going to be constant. For series, it's going to be the current that's equal to the constant, and the voltage is going to change. Some circuits, however, can't be broken down into series and parallel. Take a look at this big nasty looking guy down here where we have a couple of batteries and some resistors where maybe we can write some of them in series, but in general we can't break this down into a nice simple circuit like we could the equivalent circuits for the parallel and series connections. So what do we do for this? Well, we use what's called Kirkov Rules, and essentially what we are going to do is we're going to have kind of a loop rule, and then we're going to have a sum of voltage rule. What we need to do is, here we have three currents, 1, 2, and 3. To solve for these three currents, we need to have three equations, three unknowns. We can actually go ahead and solve this guy. One thing to kind of keep in mind here is that if we ever have two batteries in a circuit, then the one that's going to push the current around is going to be the larger one of the two. So this guy, the 80 volter, is the one that's going to determine the direction of the current. So you can kind of imagine the current coming off of the positive terminal. It's going to force it in this direction. Here it happens to also go in the same direction that this 45 volt current would go, but even if this 45 volt current battery was flipped around, it would still push the current through that battery. It's also going to push the current around in this direction right here, so this current is actually labeled in the wrong direction. Now, the first rule is the junction rule, that says the sum of the currents entering a junction is going to be the sum of the currents leaving the junction, and essentially you're going to have a junction when there's more than one pathway for current to take. I kind of like to think of it as like a water pipe T. We need to have, say a pathway here, a pathway here, and a pathway here. Essentially, if we have some water or current flowing in here, we have some water or current flowing in here, it must flow out right here. So here we would say I1 plus I2 must be equal to I3 in this example right here. Let's take a look at this circuit right here. Note that the four corners here, there is a kink, but there is no junction. Current can only come here and then go out in that direction right here. So junctions are going to occur at both A and D, and essentially what we're going to do is say, okay, look, here we have I3 flowing in, so I3 is what's coming in, and here we have written I1 and I2 coming out, so I1 plus I2. So this is kind of the in must be equal to what's coming out. Now I said in the last slide that I1 is drawn in the wrong direction, and it is, but if you go ahead and solve this guy, I1 is going to come out to be negative, and that tells you simply that it's in the wrong direction. Now, the other rule that we need to get some other equations is going to be the loop rule, and essentially I always like to write it as the sum of the potential in any given closed loop is going to be equal to 0. So take a look at this small circuit down here. If I were to say start off at D, work my way around it like that, here I have a closed loop. So if I were to kind of walk around this circuit, then what's going to happen is my voltages should all sum up to be equal to 0. So let's just kind of start off right here at D and say, hey, what's going on here? Well, I'm going to walk across this battery. I'm going from negative to positive, so I'm going to add 12 volts. Now I'm going to kind of keep on chugging along this circuit right here. I have 12 volts. Now I'm going to lose some voltage. The amount I'm going to lose is going to be equal to my current multiplied by my resistance. So I'm going to lose, that's the minus sign, the current multiplied by the resistance, so I multiplied by 400. Keep on chugging through B. I'm going to go across this 290 ohm resistor. I'm going to again lose my current multiplied by my resistance when I go across this guy. So I'm going to lose the current multiplied by 290. I'm going to come back here and reach point D. So all of these guys should be equal to 0. Kind of think of it, here I got my 0 volt side of the battery, here I've got my 12 volt side. So essentially I've lost all of my potential to those resistors, and now I can go ahead and solve this equation for current quite easily. Now, just kind of some notes on the sign conventions for my loops. I know this isn't from your book, but I like this diagram much better. If I say, let's just take a look at loop 1 for the circuit down here. If I am traveling from the negative side of a battery to a positive side, then I'm going to add the EMF when I write my sum of the voltages is equal to 0. If my loop travels from the positive side of the battery to the negative side, I'm actually going to subtract the EMF because I'm going over the battery backwards. If I happen to have my loop here, that's the guy in blue here, traveling in the same direction as the current in a resistor, I'm actually going to subtract the current times the resistance, as I did in the previous example. If my loop happens to travel in the opposite direction of the current, I'm actually going to add the current times the resistance because I'm going opposite the direction of the current. So now we can kind of come back to this circuit right here and say, okay, we've applied the junction rule. Now we have one equation, but we have, again, at 3 currents, we have 3 unknowns, we need 3 equations. So what I can do is I can use the loop rule and say pick that loop right there and pick maybe this loop right here and apply the loop rule. Sum of the voltages is equal to 0, and this one's going to give me another set of equations. This one will give me another set of equations, and then I have 3 equations and 3 unknowns, and now I can go ahead and solve this guy. Now, for the sake of time, I'm not going to do that for this example because it's solved in your book, but I highly, highly, highly recommend checking that out and making sure you understand it. So just some general notes on problem solving using Kirkov's rules. First thing you want to do is label each current, keeping in mind that the strongest battery is going to determine the direction of the current. And something else to kind of keep in mind is if you have resistors that are in series, you can say that this is going to be current 1 and this will also be current 1. You don't have to say that this is current 1 and this is current 2 because they're in series. You know that it's going to be kind of the same current. Then identify the unknowns. Typically there's going to be at least 2, maybe 3, I1, I2, and I3. Then you want to apply the junction rules and the loop rules, and you need as many equations as there are unknowns, so 3 equations, 3 unknowns. And then you just have some algebra to do. We can solve 3 equations, 3 unknowns. It can be an algebraic mess, so be careful as you manipulate it. This charging a battery example actually kind of helps highlight Kirkov's rules. Suppose I have 2 batteries and they have some internal resistance right here. What's going to be kind of the sum voltage of this current? Well, if these batteries are in the same direction, then the voltages are just going to add, just like stacking batteries together in a flashlight. So kind of conceptually, with this example right here is taking 2 batteries, just kind of stacking them up on top of each other. And we say if we know that each of these batteries is 1.5 volts, kind of say right here we would have 0 volts, right here we would have 1.5 volts, and then right here we would have 3 volts. We wanted to tack another one on, kind of like that, and then we might have 4.5 volts and so on and so forth. So really, the voltages, the EMFs are going to add when these batteries are in the same direction. So if we started off at A right here, go over this battery, now we have 1.5 volts. We're going to lose a little bit to this internal resistance. I'm going to go across this battery, we're going to gain another 1.5 volts, maybe lose a little bit because of some internal resistance, and so here I'm going to have 3 volts minus say 2 times the current and then the internal resistance of these batteries. So maybe I have maybe 2.9 volts across this guy. Now what would happen if we took two batteries and we put them into a circuit in opposite directions. Now it's kind of silly to think about it, but suppose we had a battery like this, and we took another battery and we put it backwards in there, and each of these batteries were again 1.5 volts. Let's just start off right here. Say we have 0 volts. Here we're going to go up by 1.5 volts, and here we're actually going to go down by 1.5 volts. So here at the end of the day we're going to have 0 volts. Same is true for this circuit right here. Let's start off at point A, work our way across the 20 volt battery. I'm going to pick up 20 volts, have some internal resistance, go across this battery with some internal resistance. This battery, however, is backwards, so I'm going to subtract this 12 volts, and at point C all I really have is 8 volts worth of potential, because this battery took away some of the potential that my larger battery gave me. Keep in mind that the direction of the current is going to be dictated by the larger battery, and so this battery is going to win. It's going to push current backwards through this battery, and the direction current is going to flow in this circuit's shown right here. And lastly, I'll just kind of finish batteries by saying, hey, it only makes sense to put batteries in parallel if the voltages are the same. And kind of keep in mind that, you know, these guys are in parallel, so I'm still only going to have 12 volts worth of potential across this guy because these guys are in parallel, but we can produce more current than a single EMF or a single battery.